Hi, this is technical presentation for Lab 1. Austin Haverson, Derek Zonder, and Pedro Pereira are the members of this group. Today we're going to talk about how to create equations from truth tables and optimize them. This is a very important subject to allow designers to validate and optimize their circuits, and we present by Derek. Next, Austin will discuss more about the importance on simplification equations and circuits. And he will present a real-world example on how to apply theories to solve a real problem. Austin will then show the theorems and laws you use to simplify this lab circuit. And finally, Derek will present a finished circuit using LargeSim.
We know that we can create Boolean equations from truth tables. The two forms often used are sum of products and products of sums. In short, the difference is in what rows we build the equation from. Sum of products is created from rows with true outputs. Product of sums is created from rows with false outputs and applying De Morgan's rules. Over the next couple of slides, we will create a Boolean equation demonstrating sum of products. This will be done by looking at where in the truth table the output is true and creating an expression from that row in the truth table. We will use the following truth table for our demonstration. Looking at the two highlighted rows, we see where f equals 1 are where the output is true, and we'll focus on these two lines. Looking at row 1, we can turn this into a Boolean equation. We see that A naught and B naught give us an output where f equals 1. We can represent this with A naught, B naught, which is posted to the side of the truth table. We will apply the same principle with the next highlighted row, where we see A and B naught gives f an output of 1. We will write down A and B naught. Finally, we will use an OR operation to complete the equation. We take the two equations we wrote down on the side of the column and combine them as shown. F equals A naught and B naught, or A and B naught.
So why go to all this trouble to simplify these expressions? In short, it's efficiency, and it just makes the most sense. Reducing a Boolean expression has real-world implications, and the more we can simplify the Boolean expression, we are better positioned to create faster, more efficient circuits, reduce the cost of manufacturing by using less gates and material, and save on long-term energy costs of the circuit. It is crucial to minimize expressions and limit gates. Without minimization, gates would be bulky and inefficient. Furthermore, simplification has very real-world implications. As we learned in the first lab, there are many ways to design a circuit. However, the most important factor is to capture simplicity. As we review the design of the fan alarm circuit, we will review the implications of simplifying our circuits and general applications. As we make circuits simpler, they become more efficient and they work better for us and for the user. They have longer lifespans and can perform at their topmost efficiency. In order to simplify our equation, the first step is to create a Boolean expression from our truth table. We are using the sum of products to format for this. First, the equation for the alarm. Looking at our truth table, we see that our alarm output is high when we do not have a cord input, when we have a low voltage input and no temperature input, or when we have no cord input, a high low voltage input, and a high temperature input. Based on this from our truth table, we have the equation not C, V, not T, or not C, V, and T. So using the shown method to create a sum of products to format our equation, we then use the simplification theorem, or De Morgan's law, to simplify this equation down to not C or V. Similarly, for our fan outputs, we look to our truth table and see where the fan output is high. We notice that the fan is on when we have no cord input, no low voltage input, and a high temperature input, or when we have a cord input, no low voltage input and a high temperature input, or when all of our inputs are high. Thus, this gives us the formula not C, not VT, or C, not VT, or CVT. So using the sum of products formula again, we can show that the theorems and laws and how they apply for this case. Using the distributive properties, we can find the similarities in this equation to pull out similar terms in our Boolean expression.
Now, applying the complementary law, we get fan equals V naught T or CVT. Finally, we finish with the simplification theorem, where we find the fan equals CR V naught and T. Here we see two pictures of two circuits. This is the fan and alarm circuit. We see that through simplification, we are able to go from a 3 AND gates and 1 OR gate circuit to a 2 AND gate and 1 OR gate circuit. This is the power of simplification of Boolean equations.